Well, welcome back, everybody. Today we're going to talk about Section 5, Lines, Planes, and Space. What is a line? In two dimensions, as we talked about earlier in Section 4, in two dimensions, line is defined by 2 points or 1 point and a slope. The slope defines the relationship between 1 point and the next. In 3 dimensions, we have to contend with another dimension, because here every point lies on a plane. So unlike in 2 dimensions, each point just lands on a graph, here each individual point lands on a different plane. We have to deal with scalars and vectors. So using those, we have to find equations for lines, line segments, and planes. So using those scalar and vector values, we find equations of lines, line segments, and planes in space, in 3-dimensional space. It's that third dimension that makes things pretty interesting. Lines and line segments in space. That's the first thing we're going to talk about. The line is defined as a point and the slope of that line. Each point going to infinity follows that same relationship. A line in space has a point and a vector. It defines its direction and magnitude. So knowing this, talking about this, let's look at how we find it. Let L be a line in space. Going through a point P sub 0. Its component points are X sub 0, Y sub 0, and Z sub 0. And that point is parallel to some vector. V. V is defined as these components, V sub 1 I, V sub 2 J, V sub 3 K. So the line is a set of all points X, Y, and Z for which P sub 0 and P is parallel to the vector V. So the line is a set of points. P, remember, it starts off at P sub 0 and it goes on to P, and it changes all the time following the information parallel to the vector V. So what does that tell us? So the direction of this vector, P sub 0 to P, since it's parallel to V and it's not the same lines, that means it's some scalar multiple of T, where T is some scalar multiple that depends on two things. The location of P on the line L, and two, the domain of T. The domain of T goes from negative infinity to positive infinity. It's all real numbers. So what does this tell us? What this tells us is it's going for each point. Remember, P is X, Y, Z. P sub 0 is X sub 0, Y sub 0, Z sub 0. So what this tells us is we have, since it's starting at P sub 0 going to P, we have X minus X sub 0 I plus Y minus Y sub 0 J plus Z minus Z sub 0 K. That's what this side equals. This has to equal T times the vector V1 I, V2 J, V3 K. Now, what does that equal? That tells us that it's got to be Xi, Yj, Zk. Because remember, the point keeps on moving. So if we took this and distributed it all, we would have Xi minus X sub Oi, Yj minus Y sub 0 J, Zk minus Z sub 0 K. All that equals T V1 I, V2 J, V3 K. All I did is distribute, get rid of the parentheses. So keep all the point values, X sub I, Y sub I, z sub x sub I, y sub z j, z sub k, and we move these other ones to the other side. So we have x sub 0 I plus y sub 0 j plus z sub 0 k. We're moving it to this side, so it's plus t v1 I v2 j v3 k. So we have the points. Each point, we have a fixed starting point, and then following this magnitude t, or some scalar t, we're following up those points. So that's how these get their values. So x sub I is equal to x sub 0 I plus t v sub 1 I. Now, let r of t be a position vector of any point p x y z on line L. So this tells us the position vector of any point on there. And the initial r sub 0 is the position vector of p sub 0, x sub 0, y sub 0, z sub 0. So r of t is the position vector of the point. R sub 0, so it's not really moving anywhere. It's a fixed point. We don't need that. So it's r sub 0 is the initial value point. Then, so we have those two defined. Then the vector p sub 0 to from p sub 0 to p is equal to x sub 0 I, y sub 0 j, z sub 0 k, plus the scalar multiple t, v1 I, v2 j, v3 k. Because the line starts off at a given point, and then following some vector and the magnitude multiplier, it changes positions and it grows some direction. This means this is a vector form of an equation of line. Equation of the line. So let's look at this now. Vector equation for a line. Because this would take too long to calculate, so we have to have formulas. A vector equation for a line L that goes through point 0, which is x sub 0, y sub 0, z sub 0. And is parallel to some vector v. Vector equation is r of t equals r sub 0 plus tv. where t is from negative infinity to positive infinity. That's what we just defined up earlier. This is just the way we'd write it. Is shorter. As we defined earlier, remember r is the position vector of the point, and r sub 0 is the position vector of the initial point. We see the corresponding components of our vector p sub 0p is equal to x sub 0 I, y sub 0 j, z sub 0 k, plus v1 I, v2 j, v3 k. Let's get rid of the parentheses, so we distribute that t, x sub 0 I, y sub 0 j, z sub 0 k, v1 I t, v2 j t, v3 k t. Now we could group the i's together. X sub 0 I plus t v1 I, y sub 0 j plus t v2 j plus z sub 0 k plus t v sub 3 k. Since we both of those have i's, we have x sub 0 plus t v1, y sub 0 plus t v2 j, z sub 0 plus t v3 k. So we see the x value is x sub 0 plus t v1. The y component is y sub 0 t v2, and the z component is made up of z sub 0 plus t v3. This gives us, this gives us the standard parametrization of the line L for any t negative infinity, positive infinity. So yeah, we're getting close to defining an equation so that it becomes much easier for us to calculate given the basic information. Look at parametric equations for a line. Remember what we just did, the standard parametrization of the line p sub 0, which is x sub 0, y sub 0, z sub 0, parallel to v, which is equal to v sub 1 j v sub 1I, v sub 2j, v sub 3k. So the second parameter of this is x is equal to x sub 0 plus t v1, y equals y sub 0 plus t v2, and z is equal to z sub 0 plus t v3. Again, when t goes from negative infinity to positive infinity. So this is the parameterization. But if you're asked to parametrize something, you start with the initial value, whatever your t value is, times the vector component of v. Let's look at an example here. Find parametric equations for the line through negative 2, 0, 4, parallel to v equals that, as shown below. Again, we don't need to even really see the picture. So what do we know? We know the initial point is x sub 0, y sub 0, z sub 0, which is negative 2, 0, 4. V, which is v1i, v2j, v3k is 2i plus 4j minus 2k. Using what we just defined, the parameterizations. So it's x sub 0 plus t v1. Y is y sub 0 plus t v2. Z is z sub 0 plus t v3. X sub 0 is negative 2. V is 2 t. So there's the x value for the parameterization. Y sub 0 is 0. V sub 2 is 4 t, which is 4t. And the z value is 4 plus negative 2t, which is 4 minus 2t. So our values are negative 2 plus 2t, y equals 4t, c equals 4 minus 2t. That's my parameterization. Okay, let's look at another example. Find the parametric equations of the line through p negative 3, 2, negative 3, and q negative 1, 1, negative 4, 4. So we're going from p to q. So we're looking for that vector. So p, well, we have since it's going from p to q, so it's 1 minus negative 3 I, negative 4 minus 2j, 4 minus negative 3k. This makes it plus So it's 4i minus 6j, makes it plus 7k. So that's the vector P to Q. It's parallel to the line with x sub 0, y sub 0, z sub 0. So b sub 0, since that's where it's starting from. So that is -3 to -3. The vector v1i plus v2j plus v3k is made up of these values. That's the vector we're looking at. So that's our v. So we have 4i, 6j, 7k. Now we have our p sub zeros and our v. Our parameterization is x equals x sub 0 plus v1t, y equals y sub 0 plus v2t, z equals z sub 0 plus v3t. This is x sub 0 is 3, -3, plus v1 is 4t, y sub 0 is 2, minus 6t, and z sub 0 is -3, plus 7t. And there's our parameterization. Now, one thing we have to be aware of, that it's not unique. It's not the only answer you can get. Because since t can be positive or negative, we could use any odd exponent. And it could be this similar parameterization. It'd be acceptable parameterization. All right, so as long as it's an odd function, odd power, it's going to be the same. Parametrizing line segments. So first step. Parametrize the line through the endpoints. It's in a bounded domain. Find the t value or values for the endpoints and restrict to on the closed bounded interval. All right, so let's look at an example what this tells us. Parameterize the line segments joining the points P and Q. So in step one, find the equation for the line through P and Q. P is equal to -3 to -3, and Q is 1, -1, 4. So we have to find that. So 1 minus -3i, -1 minus 2j, 4 minus -3k. 4i minus 3j plus 7k. The vector we're going to use is the first one. So we'll have -3 to -3. So parametricize, we get x sub 0. Oh, I'm sorry, it's my p sub 0. X sub 0 minus b1t, y sub 0 b2t, z sub 0 v3t. So -3 minus 4t, 2 plus 3t, -3 plus 7t. Okay, so now we have the parametrizations. That was step one. Step two. Check the endpoints. For a t value, that'll work. Okay, what is that? Oops, let me put that over here. Oops. Step two. So we know that P is equal to -3 to -3. We know that Q is 1, -1, 4. These are your endpoints. Remember that X was equal to -3 plus 4t, Y equals to 2 minus 3t, and Z is equal to -3 plus 7t. So I have to check X for both of these. So I have -3 plus 4t. This is my X. Add 3 to both sides. 0 equals 4t, so t equals 0. 3 plus 4t. So I put the 1. Add 3 to both sides. 4 equals 4t, so t equals 1. I check the y value. 2 minus 3t, 2 minus 3t. The y value here is 2. Subtract 2 from both sides, so t equals 0. Here, the y value is -1. Subtract 2, -3 equals -3t. Divide both sides, we get t equals 1. So far, so good. It's staying within the domain of 0 and 1. Z equals -3 plus 7t. C equals -3 plus 7t. So the y value here is -3. And the y value here is 4. Add 3 to both sides. 0 equals 7t. So t is equal to 0. 7 equals 7t. T equals 1. So we see that at x equals 0, the line goes through P. And at x equals 1, the line goes through Q. So that's the second part. We verified that the endpoints work. So now step 3, let's define the restrictions. On T. Well, we know at P it was 0, and at the beginning is P and the Q is the ending point. So our solution is x equals -3 plus 4t, y equals 2 minus 3t, and z equals -3 plus 7t with this restriction. So that's what we're looking for. Another example. A helicopter flies directly from a helipad at the origin in the direction of 0.111 at the speed of 60 feet per second. What is the position of the helicopter after 10 seconds? So we're looking for what is the position at t equals 10. So first off, we have to look at the beginning. The starting point. is P sub 0. It's made up of X sub 0, Y sub 0, Z sub 0. And that's at 0, 0, 0. It's at the origin. The direction to our vector is 1, 1, 1. So that's V1, V2, V3. The speed, or our magnitude of our vector, is 60 miles per second, or feet per second. So now, since we're given this information, we use this formula. It's ours is a vector. It's at time t, starting point plus t times the vector. This is the position vector now. So the first thing that you have to do here is you have to find magnitude of v. The magnitude of v is v1 squared, v2 squared, v3 squared. And they're all 1. So it's 1 squared, 1 squared, 1 squared, which is square root of 3. Now we're going to find the unit vector. That's what this part, that's the unit vector. V over radical V. So we know that V is equal to 1, 1, 1. We know that the magnitude of V is radical 3. This gives us U is equal to V over magnitude of V. 1 over, well, it's 1I, 1J, 1K. So it's equal to 1 over radical 3I plus 1 over radical 3J, 1 over radical 3K. That's my unit vector. Actually, that's the direction of flight. Because remember, it took off from 0, 0, 0. It's heading towards 1, 1, 1. So that's the direction it's going, towards the first octant. Okay. Now what do you do? We have the information we need. Into our equation. Here's our equation. So R of t is equal to R of 0. What's our beginning point? We start at the origin, so it's 0. We don't know t yet. We're looking for the equation. The magnitude The velocity we're traveling at is at 60 feet per second. And our unit vector is 1 radical 3I, 1 radical 3J, 1 radical 3K. So here we have radicals on the bottom. So we have 60T, radical 3 over 3I, radical 3 over 3J, radical 3 over 3K. I rationalize the denominators. Since they each have a 3 on the bottom, that cancels out to 60. 60 divided by 3 is 20. And they'll have a radical 3. So basically what we're doing here is we can factor out a radical 3 over 3, leaving I, J, K. 20 radical 3t I, J, K. So that is our function. At t equals 10 seconds, we get 20 radical 3 times 10. No, I, J, K, which makes it 200 radical 3 I, J, K. So the location after 10 seconds is 200 radical 3I, 200 radical 3J, 200 radical 3K. Oop. And the distance it traveled distance equals rate times time. It's 60 times 10 is 600 feet. Okay. Yeah, this is a long section. Now let's find the distance from a point to a line in space. The distance from point S, from any point S to a line in that passes through a point P. Remember, that is parallel to a vector V. Is found by finding the absolute value of the scalar components of the vector PS in the direction of a vector V normal to the line. Remember, normal means vector perpendicular to the surface at a given point. Let's call it V1. So normal means a vector perpendicular to the surface at a given point. And a unit vector is a non-zero vector divided by its length. That's what we have. That's what that is, remember? Okay, so I said earlier, the absolute value of the scalar component of the vector PS is equal to the magnitude of that vector times the sine of theta. So if you're looking for the distance of it, that's what you're looking for. So this is the distance, the magnitude of this vector PS times sine theta over the magnitude of the vector, which is equal to the magnitude of the vector PS cross the vector over the magnitude of the vector. So that's what we're going to be using to find the distance from a point to a line in space. Let's look at an example here. Find the distance from the point S, 1, 1, 5, to the line x equals 1 plus t, y equals 3 minus t, and z equals 2t. It's parametricized. So what's the distance? So we need to find PS, what V is, the magnitude of PS cross V, and the magnitude of V. We have to find all four of those things to find out what we're looking for. Okay. We have S and need to find P and V. Since L is parametricized as x sub 0 plus v1t, y is equal to y sub 0 v2t, and z is z sub 0 plus v3t. And we know that this is equal to 1 plus t y is equal to 3 minus t, and z is equal to 2t. So that tells us that x sub 0 is 1, y sub 0 is 3, z sub 0 is 0, v1 is 1, v2 is -1, v3 is 2. So P is that. And V is 1, -1, 2. Which is I minus J plus 2K. We know that P is parallel to V. It's stated that in definitions. So P is parallel to V. Okay. Bring that there. Now, since we have P and S and V, we can find PS, PS cross V, magnitude of it. So P is equal to 130, S is 115. So this one is 1 minus 1 I, 1 minus 3J, 5 minus 0K, which gives us 0, -2J plus 5K. And we know that V is 1, -1, 2. So we first have to find the cross product. So just to find the cross product, we got to find the determinant. So it's I, J, K. And P was 0, -2, 5. V was 1, 1, 2. And repeat the first two columns. 0, 1, -2, 1, 5, 2, 0, 1, -2, 1. -4I plus 5J plus 0K minus 0J minus 5i minus negative 2k. Okay, I, so we have -5, -4 makes it -9i, +5j, and +2k. So that's my cross product. Let me make sure that's it. It's -4, 5, 0, 0, -5, +2. Doesn't look right. 1, 0, 0, 1, -1, 2, 5, 2, 0, 1, -2, 1. It's -4. Okay, so the magnitude. Nine squared, 5 squared, 2 squared. 81, 25, 4. 29 plus that is square root of 110. And the magnitude of V is 1 squared, 1 squared, 2 squared, square root of 6. All right, so now we can just plug them into the equation. So then distance equals square root of 110 over square root of 6. Let me pause it and check that number again. Okay, I found my error. Yes, that's was the error was here. 1, -1, -1, -1. So it doesn't change that one, doesn't change that one, doesn't change that one, doesn't change that one. Changes this one to positive because it's 5 times -1 minus that. So it doesn't. So that just changes that one. So it changes this to 1. 25 plus, so it's 30, square root of 30. So square root of 30 over square root of 6 is square root of 5. That's the distance between the two. Sorry about that. As I always warn everybody, be careful about the signs. Be careful about the signs. And I screw it up. All right, next thing. Let's look at an equation for a plane in space. We're talking about orientation. We're talking about planes. We're talking about something called a tilt. We need that because that specifies a vector that is perpendicular or normal to the plane. A plane in space is determined by knowing a point that's on the plane and its tilt, the tilt of the plane. So what does all this stuff mean? Let's say we had a plate M. And on that plate, we had a point, P sub 0, and another point, P. There's a line, a vector normal to it, call it N. So this is now what we're going to look for, because the equation that we're looking for has to be perpendicular to that vector, that normal vector. So N is made up of AI, BJ, CK, and the initial point is X sub 0, Y sub 0, Z sub 0, and to some point. So the vector from P sub 0 to P has to be orthogonal to that vector N. So we use the dot product to determine this. This is equivalent to what we did earlier. AI plus BJ plus CK dot X minus X0I, Y minus Y0J, Z minus Z0K. Remember, this is our N dot P sub 0 to P. So we're still talking about a plane. So the plane ashes. So the plane M consists of the points X, Y, Z that satisfy this condition. Sub 0 plus C Remember, it has to be orthogonal or normal to it. So this has to be true because we have to find a normal vector to it, to the plane, and to that vector on plane. So the equation for a plane, we have three different types. The plane through P sub 0, X sub 0, Y sub 0, Z sub 0, that is normal to the vector n, AI plus BJ plus CK, has 1. The vector equation, which is found by the dot product and set it equal to 0. The component equation, which is what we just looked at, x minus a times x minus x0 plus bx minus x sub y minus y sub 0 plus c z minus z sub 0, and that has to equal 0. And lastly, we have the simplified form of the component equation, which says ax plus by plus cz is equal to some d, where d is equal to axo plus by0 c0. All we did is distribute that, move the initial values to the right-hand side, and everything else stays on the left-hand side. All right, let's look at an example here. Find the equation of a plane through P sub 0. So P sub 0 is equal to negative 3, 0, 7. That is perpendicular to n 5 2j minus k. Since we're given the components, use the component equation. The component equation is ax minus x sub 0, by minus y sub 0, c z minus z sub 0 equals 0. So P sub 0 is x sub 0, y sub 0, z sub 0, negative 3, 0, 7. And n is equal to ai bj ck, which is equal to 5i plus 2j minus k. So I always like to do, I like to label my values. X sub 0 is 3, y sub 0 is 0, z sub 0 is 7, a is 5, b is 2, c is negative 1. So I label those. Now, plug into the equation. x minus x sub 0, y minus y sub 0. So a is 5, x minus -3, 2, y minus 0, -1, z minus 7. And work it out. So 5x plus 3, 2y minus c minus 7. Distribute 5x plus 15 plus 2y minus c plus 7 equals 0. All the x's and y's on one side, everything else on the other side. So 5x plus 2y minus z equals -15 minus 7. 5x plus 2y minus c equals -22. And there we have it. That's the equation for the plane going through that point and perpendicular to that vector. Yeah, we could use any one of those if we wanted to, or we could use the simplified form. Okay, let's look at another example. Find the equation for the plane through ABC. We need to solve this, 3 things to complete this question. The first thing, the plane M. And a starting point. And a normal vector. Which we're going to have those. All we're given is ABC on the plane. So first find the normal vector. To the plane. How do we do that? We have AB cross AC. Label A, B, and C here. Oh, it's up there. So this first one is 2 minus 0 I plus 0 minus 0 J plus 0 minus 1 K. This is AB. So we have 2I minus capital, that's 0. Then we find AC. 0 minus 0I, 3 minus 0J, 0 minus 1K. So that's AC. Now to find AB cross AC, two, 0, -1, 0, 3, -1. I gotta find the determinant there. I is 2, 0, J 0, 3, K is -1, -1. 2, 0, 0, 3. Let's do my diagonals now. Zero I, 0J, 6K. Minus a -2J, minus some -3I, minus 0K. So we have 3I plus 2J plus 6K. So 3I plus 2J plus 6K is the normal vector to M. Right, next thing. Since we've got the components of the beginning points, P sub 0, which is X sub 0, Y sub 0, Z sub 0. And N, the normal vector, to the plane M. We use a component form of the equation to find the plane. X minus X sub 0 plus B Y minus Y sub 0, Z minus Z sub 0 equals 0. All right. Let's see what do we have defined already. So A was 0, 0, 1, 2, 0, 0, 0, 3, 0. We use point A as a starting point. We need a starting point so we can build from there. So P sub 0 of 0, 0, 1, and N is, well, we know that it was 3i plus 2j plus 6k. A equals 3. B equals 2. C equals 6. X sub 0 is 0. Y sub 0 is 0. Z sub 0 is 1. Yeah. So we plug those in now in our equation. A is 3. X minus 0. B is 2. Y minus 0. 6. Z minus 1 equals 0. 3x plus 2y plus 6z minus 6 equals 0. 3x plus 2y plus 6z equals 6. That's the equation of the plane M. That's what we're looking for. Yeah, it's pretty drawn out, but it's step by step by step by step. Lines of intersection. In algebra, we learned that parallel lines have the same slope. Here, two planes are parallel if and only if their normals or normal vectors are parallel. In other words, the normal of the first one has to be equal to some scalar multiple of the second. So those are parallel. Two planes that are not parallel intersect at a line in somewhere in space. Let's look at this example. Find the vector parallel to the line of intersection of the planes. We have these. This is plane 1. This is plane 2. So find the lines, parallel lines, intersection of the planes. So the line of intersection of the two planes must be or is perpendicular to the normal vectors n1 and n2 of both planes. Oh, that means they're parallel. They're parallel to the cross product of the two vectors. Yeah, so they're parallel to the cross products of the two normal vectors. So n1 cross n2 this is a vector that is parallel to the plane's line of intersection. So two lines, or two planes intersect, it creates a line. Then this cross product results in a vector that's parallel to that, right? So we're given n1 and n2. Since the planes were given as 3x minus 6y minus 2z equals 15, and 2x plus y minus 2z equals 5, we just take the front part to define our normals. Now this is normals, so this is I, J, K, I, J, K. So the n1 cross n2 has to be done by the matrix, the determinant of the matrix. I, K, 3, negative 6, negative 2, 2, 1, negative 2. So since we didn't use those equal signs, it's perpendicular to it because it's a normal part of it. Whoops. So our matrices, 3, negative 6, negative 2, 2, 1, negative 2. negative 6. So positive 12i minus 2j, 3k minus negative 6, so it's positive 6, minus negative 2, minus 12. So I, we have 2, so 14i, positive 4j, 15k. And there's our solution. That's our solution. All right, so another example. Find the parametric equations for the lines in which the planes intersect. So we're given two planes. The parametric equations of the line in which the planes intersect. So we need to find a vector parallel to the line, and the point along that line. We do this by taking the cross product of the two planes. We do that to find the vector that is parallel to the line we're looking for. So plane 1 cross plane 2. Suppose what we did last time is, remember, we needed two normal vectors, so we just took this part of each. I, J, K. So P1 is 3, negative 6, negative 2, 2, 1, negative 2. So 3, 2. Negative 2, negative 2. Oops, that's no, it's negative 6, 1. Negative 6, 1. This is negative 2, 2. So negative positive 12i minus 4j plus 3k minus 6, so it's minus minus, which makes it positive 6j minus 2, minus 2 is positive 2i minus positive 12k. So it's 14i positive 2j and 15k. Okay, so that's the vector parallel to the line. All right. Now, next thing, to find the point on the line, we find any point that is in both planes. We do this by setting any of the values of I, j, or k equal to 0. So if we set z equal to 0, no, it's x, y, z. If we said z, we saw x and y. I'm sorry. So we have the first one. We have 3x minus 6y minus 2z equals 15. And we have 2x plus y, 2z equals 5. We set z equal to 0. 3x minus 6y equals 15. 2x plus y equals 5. Three x equals 15 plus 6y. X equals 5 plus 2y. So plug it in there. 2x is 5 plus 2y. Distribute. 10 plus 4y plus y equals 5. Subtract 10. 5y equals negative 5. So y is negative 1. Plug this back in here. X is equal to 3. So our point is at x, y, z, which is 3, negative 1, 0, which is our x sub 0, y sub 0, and z sub 0. Lastly, components of the line are x sub 0 equals at, y sub 0 plus bt, z sub 0 plus ct. X sub 0 is 3. A, we determined that earlier, that's, where's that? Yeah. A is 14, B is 2, C equals 15. That equals -1 plus 2t. C equals 0 plus 15t. So those are our solutions. Where do the line and plane intersect? Let's work this to that one. Find the point where the line x is 8/3 plus 2t, y, and the point x, y, and z, that's the line, intersect the plane. All right, so first thing you do is combine the point and the equation of the plane. To find the t value of the equation for the plane. That's the first thing we do. Because we have all these, right, the line. We need to know that to find the other one. All right, so x, y, z is equal to 8/3 plus 2t, -2t, 1 plus t. So those are my x, y, and z. Three x plus 2y plus 6z equals 6. So this is my x, that goes there. This is my y, that goes there. And that's my, so we plug those in there and then solve for t. 3 times 8/3 plus 2t plus 2 times -2t plus 6, 1 plus t equals 6. Distribute, the 3's cancel, so we have 8, 6t, positive, negative is negative, 4t, plus 6 plus 6t equals 6. Combine like terms. 6 minus 4 is 2. 6 plus 6 is 12. Minus 4 is 8t. 8 plus 6 is 14. Subtract 14. 8t equals negative 8. Divide both sides by 8. T equals negative 1. So now we have t. Since we're looking for the point on the line, we know that x equals 8/3 plus 2 times negative 1. Negative 2 times negative 1. 1 plus negative 1. So 8/3 minus 2, which is 6/3, makes it 2/3. X equals 2/3. Y equals 2. And Z equals 0. So the point 2/3 to 0. That's the point on the line. Okay, now let's determine the distance from a point to a plane. If P is a point on a plane, with normal n, the distance from any point S to the plane is the length of the vector projection of PS onto N. So it's the dot product So it's the length of the projection of PS, the vector PS onto the normal vector N. Find the distance from S to the plane. To find the distance, we need a point P in the plane. A point S off the plane. A normal vector n to the plane. So first thing, we can find n by taking the coefficients of the plane, like we did earlier. Since the plane was 3x plus 2y plus 6z equals 6, our normal is simply going to be 3x plus 2y plus 6z. It's this part. We're given S. We need to find a point P on the plane. The easiest point to find is an intercept. Since we know the plane is 3x plus 2y plus 6z equals 6, to find the intercept, let's say the x-intercept, set y and z equal to 0 and solve for x. So 3x equals 6, x equals 2. So the x-intercept is at 2, 0, 0. If you wanted the y-intercept, you'd have 2y equals 6. So y equals 3, 0, 3, 0. Or the z-intercept, you'd have 6z equals 6, z equals 1, so you have 0, 0, 1. You use any one of those. So we know we have the point 0, 3, 0. That's our intercept. We have S, which is 1, 1, 3. We have N, which is 3i plus 2j plus 6k. So we need to find PS, 1 minus 0i, 1 minus 3j, 3 minus 0k. I minus 2j plus 3k. That equals my vector PS. We have to find the vector PS and the magnitude of n. So the magnitude of n is simply 3 squared, 2 squared, 6 squared. So the distance is the length of the projection of PS onto n. So the distance is PS dot n A2J 3K dot 3I plus 2n 6K over 7. So now the dot product is the product of each element. The i's, 1 times 3 over 7 is 3 over 7. Negative 2 that is negative 4 over 7 plus 18 over 7. 14 plus 3 is 17 over 7. Since its absolute value is 17 over 7. The distance from S to the plane. Now, the last thing we're going to talk about, the angles between planes. The angle between any two planes is simply the angle between their normal vectors. Remember, each normal vector is perpendicular to the plane. So if we have two interplanes that intersect, they both share the common point, and they both have normal, so the angle between the normals is the angle between the planes. Here's an example. Find the angles between the planes. First, you have to find the normals to both planes. So N1 is 3I minus 6J minus 2K. And the normal for the second line is 2I plus J minus 2K. Now we have to find the angle between them. We use this formula. N1 dot N2, magnitude of N1 times the magnitude of N2. So the first thing we have to find is the dot product. Three I minus 6J minus 2K dot 2I plus J minus 2K. So the I's 3 times 2 times I, negative 6 times 1 times J, negative 2 times K. 6I minus 6J plus 4K. So that's going to be the numerator there. We have to find the magnitude of N1. 3 squared, 6 squared, 2 squared. 36 plus 4, 49 is 7. And I had to plug in my headphones. Okay, third step is we have to find the magnitude of the second normal. 2 squared, 1 squared, 2 squared. Just here, because we're just taking the coefficients for the magnitude. 4 squared 9, so it's 3. All right, the next step, I have to find the dot product over N1 over N2. All right, so here we have 7 times 3. Remember, dot product has to be a scalar. 6 minus 6 is 0, so it's just 4. There's no I and J in there. It's just each one, the components. So the i's multiplied together. So 3 times 2 is 6. Negative 6 times 1 is negative 6. Negative 2 is positive 4. 6 cancels, so 4 over 21. So then we take the cosine inverse of 4 over 21, and we get 79 degrees. There. That finished chapter 12. Good luck, everybody. Sorry it took me so long to get to see you.